Hello, this is Professor Bennett from DigitalAudioTheory.com. This programming example comes from Chapter 14, which covers digital modeling of analog audio systems, including the impulse invariance method, bilinear transformation, as well as frequency sampling method. In this programming example, 14.2.2, we will apply the impulse invariance method to convert an analog RC filter to a digital filter. Impulse invariance is the method of characterizing an analog device by digitally sampling its IR. When we sample an analog signal, the spectrum becomes mirrored about the Nyquist frequency. Therefore, any frequencies above the Nyquist frequency that are present in the IR will result in frequency aliasing. Aliasing can be avoided by filtering the analog IR or by selecting a high enough sampling rate to fully capture the high frequencies within the IR. Let's consider a series RC filter in which we consider the voltage across the capacitor. In this configuration, the capacitor shunts high frequencies to ground, leaving us with a low-pass filter. Simply by looking up in a textbook, we can see that the IR for a series RC filter is 1 over RC times e to the negative t over RC, where t is time. The product RC is known as the time constant, and it defines the cutoff frequency as well as the decay of the IR. Using the impulse invariance method, the IR can be sampled at intervals of 1 over Fs by replacing t with n times ts in ts, shown right here. Then we apply the z-transform to the sampled IR and solve the summation using a power series. This gives a digital transfer function of 1 over RC all over 1 minus e to the negative ts over RC times z to the negative 1. The details of this are in the textbook, Digital Audio Theory, a practical guide. The next step is to determine the exact gain of the analog filter at 0 Hertz. We select 0 since this is an LPF, and so it's in the passband. We would select a representative frequency in the passband for other filter types to normalize the digital filter against that level. Solving for the gain at 0 Hertz is covered in the textbook as well. But we're going to find that the gain G is RC times 1 minus e to the negative ts over RC. This gain factor is then multiplied on the numerator of the transfer function, giving a final digital transfer function of 1 minus a over 1 minus a times z to the negative 1, where a equals e to the negative ts over RC. We can simultaneously plot the frequency responses of the continuous and digital transfer functions to visualize the artifacts that arise when converting from the S domain to the Z domain. We know that the cutoff frequency is calculable as 1 over 2 pi RC, so if we select C equals 10 nanofarads, R equal to 4.7 kiloohms, then we can expect the cutoff frequency to be at 3.4 kilohertz, with the gain at DC to be 0 dB. So here is the digital model and the analog prototype. So this comes out of a textbook, numerator and denominator coefficients. We're using freq S instead of freq Z. S telling us that this is S domain or analog domain versus what you're used to seeing for a digital model, freq Z, which tells us that this is in the Z domain. So let's first plot the analog prototype. There we have it. We should have a cutoff somewhere around 3.4 kilohertz. So at negative 3-ish dB. There we go, it's close. Yeah, 3.4 kilohertz, perfect. Then let's also plot on top of that the digital model using the impulse invariance method. There we have it in the dash. Now, we have no way filtering this continuous analog prototype. So when we do the impulse invariance method, okay, we actually are going to get some aliasing, and we see that here, where the digital model deviates from the analog prototype. That's because the analog prototype doesn't stop at 24 kilohertz. It continues on. So the energy and the frequencies beyond 24 kilohertz are actually getting folded back in, which is why we see this deviation, especially towards the high frequencies. Although it's not shown in this, since it's not shown in this example, MATLAB and Octave both contain a function called ImpInvar, I-M-P-I-N-V-A-R, that takes the numerator and denominator coefficients for an analog filter and returns the comparable coefficients for a digital filter using the impulse invariance method. In the next programming example, we'll use the frequency sampling method to model an RLC circuit with both linear and minimum phase. Thanks for watching.